Hello APC Mechanics students in Unit 1 Kinematics, Class 17 Projectile Motion, Part 3. Then Section 1 Time of Flight. Consider a projectile launched with an initial velocity v0 making an angle theta above the horizontal. So in this case, we're gonna take the positive y direction to be up. This is the initial velocity v0 making an angle theta with the horizontal. Then the initial velocity along the x-axis and the y-axis can be determined via decomposition. Vx0 would be v0 cosine theta and vy0 would be v0 sine theta. Now in this section we are interested in determining the time of flight, which is the time the projectile will remain in air before hitting the ground. The time of flight, t-flight, is the duration for which the projectile remains in air. Suppose that the projectile is launched from ground and lands back again on the ground at the same horizontal level, symmetric projectile. Then we're assuming here that the projectile will be launched at this point. It will follow this trajectory and hits back this point in which the trajectory formed is said to be symmetric projectile. Previously in class 16 we have differentiated between two types of projectile, symmetric and non-symmetric. And here we're putting a condition that the work is dedicated for symmetric projectile, and we're gonna discuss that later. Then in this case we have that the final position y is equal to the initial position y0y, because if this is the launching point and that's the landing point, then in this case this is the initial vertical position and this is the vertical final position. They are equal. Then we're making use of this equation. And we know that the vertical position time equation is given by, for a projectile, y is y0 plus v0 sine theta t minus half gt squared. Let me remind you that this is the initial position, this is the initial vertical position, and this is the acceleration along the vertical axis. And this case is given by minus g because the positive y direction is chosen to be up. Then these cancel with each other, and here we're left with 0. Now we can factor t out, and in this case we have two solutions. The first one is given by t is equal to 0, and the other one can be determined by solving this linear equation. Then if we're solving for that, isolating t or taking this to the other side, this time would be the time of flight because we've started from the equation y is equal to y0. And isolating t by taking 2 up and g down, then the time of flight for a symmetric projectile is given by the numerator 2v0 sine theta divided by g. Now remarks, notice that whenever we have an expression we need to interpret the expression in terms of the variables. Here g is constant, won't ever change. The changes might be due to v0 and sine theta. Now we know that sine theta is an increasing function from 0 to 90 degrees, which means that as the launch angle theta increases from 0 to 90, the time of flight, t-flight, increases, which means that if we're throwing a projectile, if our launch angle increases, then the projectile would remain in air for greater duration. And as the launch speed v0 increases, the time of flight, t-flight, increases as well, because t-flight is proportional for both v0 and sine theta. Then in other words, in order to increase the time of flight for a symmetric projectile or for a projectile, now I'm gonna comment about the symmetric and non-symmetric projectile. To increase the time of flight, we can increase it in two ways. Either we increase the initial speed, or we increase the launch angle. The greater the launch angle, then the greater the time of flight would be. This formula t-flight, which is given by 2v0 sine theta divided by g, only holds true for a symmetric projectile. Why? Because we started from the fact that the final vertical position y is equal to the initial vertical position y0. However, these two properties related to the variation theta and v0 holds true for a non-symmetric projectile. If you think about it, in the case of a non-symmetric projectile, if you're throwing a projectile from a cliff, then the time of flight would not have this expression. However, the time of flight would increase if theta increases and would increase also if v0 increases. Now section 2, the range of a projectile. All of the work regarding this section, the range of a projectile, only holds true for a symmetric projectile. Then here I'm putting also a condition that we're working with symmetric projectile. Consider a projectile launched with an initial velocity v0 making an angle theta above the horizontal. Now we have the document, the positive direction is up, and you know everything related to that. The range r is the maximum horizontal distance covered by the projectile with respect to the launching point. Then basically here I'm defining what is meant by the range. The range is the maximum horizontal distance. Then graphically that would be the range. The range is the maximum horizontal distance measured with respect to the launching point. Suppose that the projectile is launched from ground and lands back again on the ground at the same horizontal level. For sure we're talking at the same projectile. Then suppose we have launched the projectile from this point, point A, and it will reach this point, which is the point B. This horizontal distance represents the range R. Then basically we are interested in determining the expression of the range. Then also we can start from the fact that y is equal to y0. Then here the final vertical position and the initial vertical position cancel out and we're left with 0, and we can factor t out, and we have that the time is given by 2v0 sine theta over g, which is the time of flight. Then basically we have what we have done here so far is we have determined again the time of flight. Now we're gonna make use of this equation and we will replace it in the horizontal position time equation. We know that for a projectile the motion along the x-axis is given by uniform motion because there is no acceleration, and the final position is equal to the initial position plus Vx multiplied by t, but we know that Vx is constant along the trajectory and it's given by V0 cosine theta. Now we will replace this time here. Now the position time equation is given by that. The initial launch point coincides with the origin, which makes x0 to be 0, and the final position would be given by the range r. Then x will be replaced by r and x0 would be replaced by the origin, which is 0, and in this case r would be given by v0 cosine theta multiplied by t. But remember, this is the time of flight because we're calculating the range, and the range happens at the landing point. By that the lapse time or the duration would be given by the time of flight. Now here, multiplying v0 by v0, that would be v0 square. We have in the numerator 2 and sine theta multiplied by cosine theta. Then that would be the expression of the range. Now let me simplify it more even further. We have an identity given by sine 2 theta is given by 2 sine theta cosine theta. Then sine, let me write it here, sine 2 theta is equal to 2 sine theta cosine theta. This is known as one of the linearization's identity related to trigonometric function, which switches the angle from the double to theta. So this is just an identity, and by that, if we make use of this identity in the numerator, the range would have a compact form given by v0 square sine 2 theta divided by g. Now then, the range for a symmetric projectile is given by r in the numerator v0 square sine 2 theta divided by g. And now, because this expression depends on the variable v0 and theta, it's healthy to interpret the variation of the range in terms of these parameters. The first thing that we can say, as the initial launch speed increases, the range r increases. Then basically, if you're throwing something, in order to increase your range, you need to give it a greater initial velocity, and this is very intuitive. However, what is not intuitive is how the range can be related to the launch angle, and let's check this together. Now you know that the sine function and the cosine function, they have a maximum value equal to 1 and a minimum value is equal to minus 1. So basically this function has a maximum value equals to 1, which is basically this, and this happens whenever the angle is given by 90 degrees. So now we're gonna say that this would be maximum if the angle, which is here in this case 2 theta, is given by 90 degrees. The angle is 90 degrees. Here the angle is theta, but here we're talking about the angle which is the double of theta. So let me repeat and say the function sine 2 theta has a maximum value for 2 theta is given by 90 degrees, which means that theta would be 45. then the maximum range R max is attained for an angle of 45 degrees, and this is not intuitive. In a sense that if you want to increase your range, the first thing that you're gonna do, increase your launch speed, but moreover, you can launch the projectile at an angle with respect to the horizontal given by 45 degrees. That would give you also the maximum range. Then the range can increase in two ways, either by increasing your initial velocity and or launching your projectile at a specific angle given by 45 degrees, which is a mid angle between 0 and 90 degrees. Now another thing here important to notice, since the expression of the range R, so we're getting back to the previous expression in which sine 2 theta is given by 2 sine theta cosine theta, over G includes both sine theta and cosine theta, then any two angles that sum up to 90 degrees have the same range. In other words, a projectile have the same range for two complementary angles given by theta and 90 minus theta. And here let me explain something important related to mathematics. Now let me consider the angles given by 30 degrees and 60 degrees. These two angles are complementary angles because they add up to 90 degrees. So now you can try the following product given by sine 60 multiplied by cosine 60, you're gonna get a number. And now you can try again by doing sine 30 multiplied by cosine 30, you will get another number. And if you compare these two numbers, they would be perfectly equal. And this holds true for any two angles that sum up to 90. Let me give another example. Suppose now our choice goes with, let me say, 20 degrees and 70 degrees. So if you try on the calculator sine 20 multiplied by cosine 20, you're gonna get a number. And if you try again sine 70 multiplied by cosine 70, you will get another number, and surprisingly these two numbers are equal. How this would affect our result, let me explain more. Suppose a projectile is shot with the same velocity by two different angles, 20 degrees and 70 degrees, then they're gonna have the same range. In the first picture, we're shooting the projectile with the same initial velocity. Let me say that here, for example, the initial velocity is given by, let me say, 15 meters per second. And here is given by also 15 meters per second. But what is the difference between both is that the first one is given at a launch angle of 20 degrees and the other one is given at a launch angle 70 degrees. Believe me or no, both projectiles will have the same range. Alright? But what is the difference between both is the time of flight is different for both. Actually, because now we know that the time of flight increases when theta increases, which means that this, so let me say this have a time of flight given by t 70 degrees, and this have a time of flight given by 20 degrees. Although both have the same range because these two angles are complementary, however, what is different is that the time of flight for t 70 degrees would be greater than the time of flight for 20 degrees. This holds true for any two angles that sum up to 90 degrees, like 30, 60, 35, 55, and so on. You can choose any two angles that sum up to 90, any choice, 10, 80, 15, 75, 20 and 60, 20 and 70, any two angles. That would give you the same range. However, the projectile with a greater angle would have the greater time of flight. Now let me also mention something very important. How does the range varies? Now let me split this angle into two parts. From 0 to 45 degrees, that would be 45 degrees. And let me split this as well. From 0 to 45 degrees. And that would be, so this, okay, that would be to 90 degrees. Let me erase that. Okay, this would represent the measure of 90 degrees. Now if you're looking at the variation of r, the range r, it's gonna increase for values of theta from 0 to 45 degrees, reaching its maximum at 45 degrees. So we agreed that the maximum range occurs at an angle of 45 degrees. However, if the angle theta is increasing from a 0 value to 45, that would increase the range, reaching its maximum at 45 degrees. However, now the range r decreases for values of theta from 45 degrees to 90 degrees, starting from maximum value at 45. So we know that now the range is attained at an angle of 45 degrees. Now going from 45 degrees to 90 degrees, that would make the range to decrease. So going from 0 degrees to 45 degrees, this makes the range to increase, reaching its maximum r max at 45 degrees. Then going from angles of 45 degrees to 90 degrees, that would make the range to decrease back again. And if you think about it, if you're launching the projectile vertically upward, that would produces no range because it will be launched upward and it will land again at the launching point. Then let me do a recap here. The range r is attained at a maximum range r is maximum at an angle 45 degrees. From 0 to 45 the range increases, whereas going from 45 to 90 the range decreases. And remember that again and again, the range is maximum at 45 degrees. Now section 3, prerequisite for a projectile motion. Almost a variety of problems in physics require some prerequisites. And now here I'm gonna introduce some notion related to projectile. What is meant by prerequisite? That sometimes it's difficult to solve the problem unless you have seen it previously. Then for a projectile motion, we're gonna assume the following. Idea 1, a projectile launched from a cliff level surface have a launching angle theta to be 0, theta is equal to 0 degrees, and in particular Vy0 is equal to 0, 0 initial velocity, vertical velocity. Let me explain that. So in the first figure, we're launching a projectile from a table, which is a level surface. Here, we're launching a projectile, let's suppose, from a building, from a level surface. And here, let me suppose that we're launching a projectile from a cliff. In this case, if this is the horizontal, and because the projectile is being launched along this level surface, then its velocity vector would be parallel to the horizontal, which means that theta would be equal to 0 here. So the launching angle is 0. So more importantly, Vx0 would be equal to the magnitude of the total velocity, and Vy0 in this case would be 0 because the velocity vector at this point and the launching point has no vertical components. Similarly here, let me repeat it again. We're launching the projectile from a building which is a level surface. At this point, which is the launching point, it will have a velocity like this. Now this is the horizontal and that's the vertical. Now V is completely parallel to the horizontal, then the launch angle theta cannot be represented here as 0, which means that Vx0 will be completely the total velocity, which is V, and Vy0 would be 0. Now also let me repeat the explanation here. Here we're launching the projectile from a cliff, let's suppose. Then the initial velocity is parallel to the horizontal, and that would be the vertical. We notice that the initial velocity makes no angle with the vertical, so theta is 0. So what does this mean? That Vx0, the horizontal component of the velocity at the point of launch, which is the initial point, that would be the total velocity, which is V0 in this case. And the vertical, so let me say this is 0, this is 0 as well, this is 0, and this is 0 as well, the initial velocity. And for the initial vertical velocity, that would be 0 because the initial velocity makes no angle with the vertical. So this is an important thing to notice. Whenever we're launching a projectile from a level surface, the launching angle would be 0. This is 1. The initial velocity along the vertical direction would be 0. And Vx0 would be the total initial velocity. And let me also say that in this case, the time of flight and the range formula breaks down. Why? Because here the trajectory is gonna be something like that. Here the trajectory is gonna be something like that if it lands at the point T. Here it's gonna be something like that. And if you notice carefully, all of these projectiles are non-symmetric projectiles, and the formula that we have derived for the time of flight and for the range, they are just exclusive for the symmetric projectile. Okay, now let's move on to idea 2. A projectile launched from an incline or a ramp have a launching angle theta related to the angle of the ramp. Okay, let me explain that. Now here in this figure, in the first figure, the object initially was at point B. It has given an initial speed and it will go up to point O. Okay, the speed at O would be different than the speed at B. But the thing is that after the point O, the motion of the object will be a projectile, and the initial velocity will be related to the velocity at the point O. But what would be the launching angle? Since this is a ramp inclined by alpha, then the launching angle would be equal to the angle of the ramp, which is alpha. So let me repeat and say again, the object initially was at point B. It will go up the ramp, reaching the point O with a speed less than that of B. Due to the pull of gravity, we're not discussing here friction, so the speed will be reduced at the point O. Now after the point O, the motion of the object will be a projectile motion given an initial velocity v0, which is the same at this point. Now what about the angle? The angle here would be the same of the angle of the ramp. Similarly here, the object has started at B with an initial velocity. It's gonna go up the ramp, reaching the point D. After the point D, the trajectory will be a projectile with a velocity vt, which is the same velocity at the point D. But what about the angle? Since the angle of the ramp is 30 degrees, then the launching angle would be 30 degrees, even if it's not explicitly mentioned in the exercise. Now here, at the roof of a house, we have an object starting at point A. From point A going to point O, it will gain some speed, and we know how to derive that. However, now after point O, as you can see that the motion of the object will be a projectile motion. And okay, now we're interested in the angle theta. What would be this angle theta? This angle theta would be the same angle that the roof makes with the horizontal. Alright, which is the same idea basically that have been represented here. And notice that all of these trajectories are cases of non-symmetric projectile. Then the formulas that we have derived for the time of flight and the range here, they will break down. Now section 3 or idea 3, a projectile launched from a moving body have an initial velocity same as the moving body. So here we have an airplane. It will drop down a package. Now initially the airplane is moving horizontally, so it will release the package. What is the initial velocity of the package? This is related to the velocity of the plane. So because the plane has a velocity vector v, which is horizontal, then the package at this point, the point of release, will have a velocity which is like that, which means in this case the launch angle would be 0. So vy0 would be 0, and vx0 would be completely equal to v, which is the speed of the airplane. Now here the airplane is not moving horizontally, however it has a velocity vector which is v0 like this, and it will drop down a projectile. What would be the initial velocity of this projectile? It would be the same as the airplane. This angle alpha is related to the angle that the airplane makes with the horizontal, and the value v0 would be equal to the speed of the airplane at the moment it drops the projectile. And you know that in this case the time of flight and the range formulas break down, because this is the case of a non-symmetric projectile. Now section 4, maximum horizontal distance. Consider a projectile launched from a cliff, non-symmetric projectile. Now here we can discuss two things. We have defined or introduced the range as the maximum horizontal distance, but remember that definition for a symmetric projectile. Here we can do two arguments. We can say that this is the range, or this is the range. However, according to our definition, because the range is related to a symmetric projectile, then that would be the correct definition of the range, and this is not range. So let me repeat and say again, the range would be the horizontal distance between the initial point and another point. It might be the final point, but this is not the case here. So at a later time t, such that the initial point and that point would lie on the same horizontal level. Then the range is related to the part of the projectile which is symmetric. Now what about this distance? This distance is said to be the maximum horizontal distance. Now that would be the range which is related to the symmetric part of the projectile. And in this case, the range r is not the maximum horizontal distance. That would be the maximum horizontal distance from the cliff. So we're launching the projectile from the cliff. It will land on the sea level. This distance from this point, which is vertically lies along the origin. So we're measuring the horizontal distance from this point to the landing point. That would be the maximum horizontal distance from the cliff. And in this case, let me remind you that the range occurs for a particular angle which is 45 degrees. However, in this case, the maximum horizontal distance from the cliff is attained at an angle between 0 and 45 degrees above the horizontal. So if you want to attain the maximum horizontal distance, this is attained for an angle between 0 and 45. What is the value of this angle? This depends on the height of the cliff. So I cannot give you any specific angle for the maximum horizontal distance. For the range, because it's symmetric, we can always claim that it is at 45 degrees. However, if we're talking about maximum horizontal distance for a non-symmetric projectile, this maximum horizontal distance occur for a launching angle between 0 and 45, but we cannot specify the value of this angle because this depends on the height of the cliff itself. So let me do a recap. We're interested in the range or maximum horizontal distance. If we're talking about a range which is for a symmetric projectile, the range is maximum for a specific angle given by 45 degrees. However, if we're talking about maximum horizontal distance, we cannot specify the angle. However, I can tell you that it occurs at an angle between 0 and 45 degrees. Now exercise 1, an object is thrown with velocity v from the edge of a cliff above the level ground. So it will follow the following trajectory, and this is the case of an unsymmetric projectile. Neglect a resistance in order for the object to travel maximum horizontal distance. We're talking about this. Hitting the ground, the throw should be at an angle theta with respect to the horizontal, and we know that in this case it should be greater than 0 but less than 45 degrees above the horizontal. So this is the case which is part C. Because we've said previously we're measuring the angle above the horizontal and not below the horizontal, which makes E a wrong choice. Now exercise 2, a ball is released from the top of a ramp and rolls off a table as shown on the figure. Point P is the location at which the ball has just left the edge of the table. Using the coordinate axis shown, which of the following is correct regarding the vertical acceleration AY and the components of the velocity of the ball at point P? Now, regardless of any point, we know that for a projectile, AX is always 0 because there are no forces acting along the X direction. However, for the vertical acceleration, that would be either plus g or minus g, and that depends on the positive Y direction. Y is up, which means that AY is negative g. So in this case, AY is negative because we're interested in comparing the value of AY to 0. So now we know that AX is 0. AY is negative, and we're interested in Vx and Vy. So it's gonna have a Vx in the positive direction, so Vx would be positive. Now because it's being launched from a level surface, we know that in this case the launch angle theta would be 0, which means that the vertical component of the initial velocity would be 0. Now let's choose the correct answer. So we have that AY is negative, so we're interested in this and in this. Now Vx is positive in both cases, that's fine, but Vy is 0, so A would be the correct choice. Now exercise 3, which is the exit ticket of today's class. A projectile is launched from level ground with initial speed v0 at an angle theta with the horizontal. If air resistance is negligible, how long will the projectile remain in the air? So we're talking about a symmetric projectile in which it's launched from a level ground and it will reach the ground back again. We're interested in the time because they're asking us for how long, so we need the time of flight. Suppose I don't remember the explicit expression of the time of flight, we can derive it quickly. We know that the time of flight happens from the equation that the final vertical position is equal to the initial vertical position, and we know that the vertical position is given by y is equal to y0 plus v0 sine theta t minus half gt square. Here we're assuming that the positive direction is up, so ay is negative. This cancels with that, then we're left with 0 is equal to v0 sine theta t minus half gt square, and we can factor out t. That would be v0 sine theta minus half gt, and we're solving for that because t is equal to 0 represents the launching point. Then v0 sine theta minus half gt is equal to 0. We can move this to the other side. That would be v0 sine theta equals to half gt. 2 goes up, g goes down, then t would be given by 2 v0 sine theta divided by g, and the correct answer in this case, it is E. It is important that you acquire both skills. Try to remember the explicit expression of such quantities like time of flight and the range, and in the case of if you forgot, try to remember how we derived such expressions. Okay, and that's it for me in this video, guys. See you soon in a new one.